Good morning everyone, thank you for joining me for this video. I am Mr. Ish. Directly preceding this video, I introduced you to a bunch of questions, trigonometric integration questions, which had increasing complexity from the first to the fourth question that was presented in that video. And I presented the idea that trigonometric integrals can get quite complex. In essence, all I was doing was introducing you to the fact that these integrals can get complex, kind of creating a framework or reason why I should present this video, where now we look at a framework to overcome the complexity of those integral types. A framework meaning a bunch of rules that you can use to help achieve antiderivatives for some tricky integration questions which you'll see involving trigonometric functions. And you know, I've usually focused more on tangent and secant and less so with regards to integration for cosecants and cotangents, simply because secants and tangents are more commonly seen. But in this video, what we're looking at are questions of this type, and we'll be looking at not just secants and tangents, we'll be looking at cotangents and cosecants as well, where m and n represent exponential powers, where m and n not are only exponential powers, but they can be of even or they can be of odd nature. That's what we want to look at over here. These are more commonly seen, these type of questions. These type of questions are less commonly seen, but in terms of overcoming the complexity of these trigonometric integrals, the framework, the rules are exactly the same, and everything will stem with regards to making a good u substitution. Remember the polynomial substitution technique, u is equal to something. We'll have to learn how to make a good u substitution, and of course we have to keep relying on this identity as we will so for this one. These two trigonometric identities are just too inherently involved in these type of questions that you have to know them, and everything will stem from this framework which we will develop. Let's start by laying down the groundwork or the framework, or you can even say the rules which employ or affect these type of questions. You know, there are similar type of questions involving sine and cosines, but these ones are technically more difficult. Where m and n tend to be even, you have to do a certain set of steps. And you know, in terms of tangent and secants, cotangent and cosecants, the only difference between these with regards to their derivatives or their antiderivatives is these tend to bring in minus signs and these tend to remain positive. But let's look at the framework. At any time you're seeing questions like this where the m and n, the exponential powers, are of even character, you want to do the following steps. Let's lay out the rules here. You want to save at least one secant x or cosecant x depending on the type of question we have. And you know, we're looking here at the even forms where m and n are even. You want to save at least one secant x, one cosecant x, and we can just put this in terms of, let's just put it in terms here of the square. You want to save at least one of these because these are manageable in the substitution technique. So it's not just secant x, cosecant x, but it's secant square x and cosecant square x. What's another thing we want to do? You want to think about those trigonometric identities and you want to use this. Depending on the question, tan square x plus 1 or cotan square x plus 1. Substitute these in places of the secants and the cosecants, all to convert function in terms, or rewrite your function in terms of tangents or cotangents. If you will substitute in this type of question or in this type of question all of these secant squares or the cosecant squares with these, you've essentially converted an expression, except for the one of these which you are saving. You've essentially converted more of your secants and more of your cosecants into tangents and cotangents by means of this substitution, and you will see how beneficial it is. Lastly, all of these questions will go through some form of polynomial substitution technique, and in that you want to do u is equal to tan x substitution, or you want to do u is equal to cotan x. When you do the next part, you'll be du is equal to secant square x dx, or here du will be equal to minus cosecant square x dx. You see how the cotangents and cosecants bring in the minus signs, tangents and secants do not, but that's fine. Minuses are no more of a problem than our positives. And then you know the basic polynomial substitution technique extends from here. But these are the things you want to do. For these type of questions which have even exponents, save at least one secant square x or one cosecant square x, depending on the question form. You want to use either this or this to get more of your function converted into either tangents or cotangents. Lastly, think about these in terms of your substitutions. That's the framework here for these even forms. Now, slightly more complex but not excessively so are the questions of this form where m and n are odd. Here you'll do a certain different set of rules or frameworks similar to previous, but they're different in terms of their nature. This is what you want to do. You want to save at least, I won't write the word at least, but save at least one tan x secant x factor or cotan x cosecant x factor from the question that you have, and just put it aside into your integral. And you'll see how beneficial this is when we show you examples. So you want to do this as your first step. With regards to the trigonometric identities, tan square x plus 1 equals secant square x, or cotangent square x plus 1 is equal to cosecant square x, you want to use those type of identities, except here you do secant square x minus 1, or depending on the question type, cosecant square x minus 1, to convert most of your question. Alright, to convert, that's his right function here in terms of our question. To convert function in terms of secant or cosecant based on the question form that we have. That way you're eliminating most of these tangents and you're eliminating most of these cotangents, and you're bringing in secants and cosecants into your question form. Lastly, the substitution you want to do over here is u is equal to secant x, because all of these questions will somehow most likely involve a polynomial substitution technique, and except you'll do u equals this. Therefore du is equal to secant x tan x dx. Think about it. When you're doing u is equal to secant x and du is equal to this right here will cancel out this factor you've saved aside. Or based on the question form, u is equal to cosecant x, and then du is equal to minus cosecant x cotan x, and again this factor you've plucked out and saved will get cancelled by this substitution you're doing, and then you'll take it down to completion. So keep in mind, this is the framework for questions of this sort. We're not looking at sine and cosines, but questions of these sorts where m and n are exponential powers of either even or odd. The framework over here and the one previously presented are the ways and the means by which you'll handle these questions. So as our first example, we will look at this question, and here we're seeing cotan and cosecant. We cannot always be dependent on practice involving only tangent and secants, and these type of functions here don't add any extra complexity other than maybe basic unfamiliarity we have with them because we don't see them too commonly, or they may bring in negative signs which the other functions will not. But that's fine, we'll deal with it as we see it. And here the exponents are even, so we have to think back to our frameworks that we have for even type of questions, where the question exponents are even. What are some of the things we can do over here? We need to try to convert everything here in terms of cotangent, but we should start by saving at least one cosecant square x. Remember the rule said save at least one cosecant square x or secant square x based on the function question. And here what we'll do is cotan 4x cosecant square x, cosecant square x, and cosecant square x. This is the cosecant square x that I'm saving, and dx. This I could have just written here cosecant to the 4x, which is fine, but the only reason why I'm writing it here is because I'm going to do the second part of those rules where you do the substitution. Remember, cotan square x plus 1 is equal to cosecant square x. I'm eliminating the x's over there, but we're doing that. Cosecant square x is equal to this. So this right here will substitute into each of these, and essentially, except for this part, everything will be converted into a question in terms of cotans. So we'll have cotan 4x, then we'll have cotan square x plus 1, but since we have this twice, we can just put a square over here outside the parentheses. It's exactly the same as that, writing it individually. And then we have this cosecant square x, which had to be saved based on the framework. Now the next step, remember initially you recognize that you're dealing with even and odds. We're dealing with even. Then you recognize that you have to save or set aside at least one of these, cosecant square x. Then you think back to your identity and you start substituting those to start making the question in terms of the cotangent function, or tangent if it was that type of question. Now the third thing you have to do is a substitution. You have to substitute for cotan x. Remember, either you substitute for tan x or cotan x. Here we're doing u equals cotan x, therefore du is equal to minus cosecant square x dx, and dx is equal to minus du over cosecant square x. Remember, you should be comfortable with these level of questions, and bring this in. If u is equal to cotan x, well, let's bring it in. We have u to the 4, and here I have u square plus 1 all square, right? U square plus 1 all square, and here I have cosecant square x and du over cosecant square x. This minus I'm going to bring right out here at the very beginning. Not too hard, initially hard, but with time it becomes easy. Open up this, you have u to the 4th multiplying with this. U square plus 1 all square is u to the 4th plus 2u square plus 1 du. Again, as I said in the previous video where I talked about the complexities, we're converting this type of function into a polynomial function, and then you resubstitute back after you've done the integration. You have minus integral u to the 8 plus 2u to the 6 plus u to the 4. Once you've come to this step, it's easy. You'll end up getting minus u to the 9 over 9 plus 2u to the 7 over 7 plus u to the 5 over 5 plus c, and in the final step you just resubstitute. We'll bring the minus right here on the side, and u is equal to cotan x, cotan to the power of 9x over 9 plus 2 over 7 cotan to the power of 7x plus 1 over 5 cotan to the power of 5x plus c, and that right there represents a good final answer. Okay, let's look at this question. Cotan to the power of 5x, cosecant to the power of 9x, and we have to integrate this. The exponential m and n values are odd, so it's going to be slightly more complex, but it'll be manageable. Thinking back to the rule and the framework I presented, where the exponents here are in the odd character, we need to set aside at least one cotan x, one cosecant x. For this type of question, that's what we set aside. And you know, if the question involved tangents and secants, we'd be setting aside a tangent x and a secant x, but here we set aside a cotan and a cosecant x. When we set it aside, we rewrite our integral with one power reduced because we've plucked that out. Cotan 5x becomes cotan to the 4x. Cosecant to the 9x becomes cosecant to the 8x, and then we still write the factor out which has been plucked out because it is very much part of the question. I'm just parenthesizing it here so I keep in mind that I've pulled it out. Now we have to think back to the Pythagorean trigonometric identity, cotan square x plus 1 equals cosecant square x. We have to try to convert this question into more of these cosecants by using the Pythagorean identity I've just said. If cotan square x plus 1 is equal to cosecant square x, then cotan square x must equal cosecant square x minus 1. So we have to substitute that. Cosecant square x minus 1 substitutes for each of these cotan square x. But I have two cotan square x, because cotan square x times cotan square x gives me cotan 4x. I have two of these, hence I have a square over there. Think about it, it's nothing out of the ordinary I'm doing over here. Cotan square x is equal to cosecant square x minus 1. Since I have two of these, I must have two of these, right? Two of these. And that's exactly what I've done. Now we have cosecant to the 8x, and we still have this factor which will get eliminated, as you will see, with the substitution. So the first step was to pluck this out and set it aside. Second step was to involve these identities to make the question more so in terms of cosecants. The next step is to use this substitution. U is equal to cosecant x, or it would have been secant x for that type of question where you have tangents and secants. Then du is equal to minus cosecant x, cotan x, dx. And you know, this brings in the minus sign, du or minus cosecant x, cotan x. And that's the beauty of this. This thing will cancel out with that when you do your substitution. Let's do the substitution and involve it in. If u is equal to cosecant x, where we have cosecant x, we should put a u. U is equal to cosecant x, but cosecant square x is u square. Then I have a minus 1, and then I have this whole square. Then I have u to the 8, right? U to the 8. Here I have a cotan x, cosecant x du over cosecant x, cotan x. Don't forget the minus sign, bring it out here. These will cancel out. You essentially have to open this and multiply with that, and let's do it. I'll have u to the 4 minus 2u square plus 1 times u to the 8 du, and again this expression has been converted into a polynomial expression, which is easy. When you open this up, you'll have u to the 12 minus 2u to the 10 plus u to the 8 du. We'll integrate it and resubstitute back in the same step, so we won't be doing too much more writing. Let's not forget the minus sign. Here's my minus sign, and I can just put a parentheses here because the minus will affect everything. U to the 12 will become u to the 13 over 13, and u here was cosecant x, so it'll be cosecant to the 13x over 13. U to the 10 will become u to the 11 over 11, right? Minus 2 over 11 cosecant to the 11x. U to the 8 will become u to the 9 over 9 plus cosecant to the 9x over 9 plus c. If you want, you don't have to, you could do a common denominator, bring everything under a unifying denominator. At the end you could isolate a cosecant 9x and then simplify everything on the top, and you can do all of that algebra. If you want to present an answer in a more condensed form, you could do all of that, but you can even stop over here and that's fine. I've presented two examples already involving cotan and cosecant, even and odd exponents. Let's look at two examples involving tan and secant with even and odd exponents. Once you look through the four examples that I'll present in this video, I think very comfortably you'll be quite adept at these type of questions, and then you can challenge yourselves individually as you want. Here we have even exponents, and what you remember with regards to the rules, the frameworks I presented for even format questions, well, we'll start by doing this. We have to save out at least a single secant square x and rewrite our question to reflect that. The secant 8x will become secant to the 6x and secant square x dx. See, I've saved this out and I've brought it out, because this right here will get cancelled out with that substitution we'll make down the road. You want to present your question more so in terms of tan, therefore you must use that Pythagorean identity, tan square x plus 1 equals secant square x. So wherever you have secant square x, you can plug in a tan square x plus 1, and we'll do that. Tan square x, and we have tan square x plus 1. Each individual secant square x is equal to tan square x plus 1. That's each individual secant square x. But secant to the 6x represents 3 of those secant square x, so we can put 3 over here. Because secant square x times secant square x times secant square x is to the power of 3. This is just laws of exponents here at play. Secant square x dx. Now, the first step was to set aside the secant square x. Second step was to involve some sort of Pythagorean identity to convert your question into more so in terms of one function with regards to the other. The third step must involve some sort of substitution. Tan x. U is equal to tan x, du is equal to secant square x dx, and dx is equal to du over secant square x. Remember, the whole purpose of this third step is to cancel out that which you saved. If you're not able to cancel something out as a result of this polynomial substitution, then somewhere along the way you've made a mistake and you have to backtrack. If u is equal to tan x, then we must do the substitutions. Tan square x becomes u square. Tan square x plus 1 becomes u square plus 1 to the power of 3. Secant square x, which will cancel out with this du over secant square x, and we've cancelled it out. This right here looks like an a plus b all cubed. Think back to your factoring videos, a plus b all cubed. There's a specific format for that. Is equal to a cubed plus 3a square b plus 3ab square plus b cubed. And you have to run this through that. When you open it up, you'll get u square, and here you'll get u to the 6 plus 3 u to the 4 plus 3 u square plus 1 du. If you've done this correctly, I believe I have, then you'll end up with the right answer. And then you open it up, you'll get u to the 8 plus 3 u to the 6 plus 3 u to the 4 plus u square du. What we'll do here in this last step is integrate and resubstitute. U to the 8 will become u to the 9 over 9. Think back to the polynomial integral videos. These type of integrals are very easy to do. Just think these are x's in terms of u's. U to the 8 will become u to the 9 over 9, but u was tan x. So it will become tan to the power of 9x over 9. 3u to the 6 will become u to the 7 over 7 plus 3 tan to the power of 7x over 7. 3u to the 4, u to the 5 over 5. That will become 3 tan to the power of 5x over 5. And lastly, u cube over 3 tan cube x over 3 plus c at the end, the constant of integration. And that represents a good final answer for this question. You could generate a common denominator. get everything under a unifying denominator, then you could probably isolate a tan cube x and rewrite everything, but you can leave everything in this way and it should be fine. We'll end the video with this question, and that should wrap it up in terms of all the practice we need with regards to the framework I've already presented at the beginning. The rest will just basically follow this process, and you don't need to see an innumerable number of examples to get a handle of this technique. These few examples should suffice. When you're looking at something of this form with odd exponents, you want to pluck out a secant x and a tan x from the very beginning and rewrite your function to reflect that. The 9 becomes an 8, the secant cube becomes a square x, and then you've plucked out a tan x and a secant x, and that's the very first step of your procedure and the whole process over here. Now you want to try to convert everything more so in this form. Think back to the identity. Secant square x is equal to tan square x plus 1. But tan square x is equal to secant square x minus 1. You want to get rid of these tans and write them in terms of secants. So wherever you have a tan square x, you should really be thinking of a secant square x minus 1. Secant square x minus 1 now will be here to the power of 4. Here we'll have secant square x. Here we have a tan x secant x dx. And now the third step, we'll have a little bit of a complexity over here only because of this 4 to the power of 4. We'll have to expand this out using the binomial theorem. It'll be fun, but it won't be too hard. And then now the substitution is what? U is equal to secant x, because we need to somehow cancel this term. If u is equal to secant x, then du is equal to secant x tan x dx. And you can see very clearly tangents and secants don't bring in minus signs like the cotan and cosecant do. Du over secant x tan x. So this right here represents our substitution. U is equal to secant x. Then this becomes u square minus 1 to the power of 4. Write it more cleanly. U square minus 1 to the power of 4 times u square du. Skipping a step over here because this thing right here would cancel out with this. I'm not writing it out here just to cancel out. I'm cancelling it out right here because it would. We have to expand u square minus 1 to the power of 4, and let's do it. Let's quickly go back to our binomial theorem, expand it out, then we'll write it out, and then we'll plug it back in. We'll have 4, 0, u square, we'll have 4, and we'll have 1 to the power of 0 minus. You can refer back to my binomial theorem video. I have it presented, and you can see what the technique word there is for this. Because there's a 4 over here, you must have 5 terms. And it's always plus minus for those binomials which have a minus sign over here. Alright, let's write it. 4, 0, combinatorial coefficient here will just be a 1. You'll have u to the 8. 4 and 1, well, we'll have 24 divided by 6. We'll have a 4 u to the 6. Here what will we have? 6 u 4. Here we'll have, remember binomial, Pascal's triangle, there's a symmetry of these coefficients, especially when you don't have coefficients here, then you'll have symmetrical coefficients. Here you'll have 4u square, and lastly here we'll have 1. It looks right to me. So this is what we are supposed to get out of here, and let's erase everything and plug that in. We'll erase this entire part here on the top and bring it into picture. Then you can realize now why precalculus is necessary to calculus, because all of these little factors come into play. u8 minus 4u to the 6 plus 6u to the 4 minus 4u square plus 1. It still has to multiply by this u square du. Now we have to open this up. We'll have u8 times u square is u to the 10 minus 4u to the 8 plus 6u to the 6 minus 4u to the 4 plus u square. Of course, I admit this question became a little complex. When you open this up, you will have u to the 11 over 11 minus 4u to the 9 over 9 plus 6u to the 7 over 7 minus 4u to the 5 over 5, and these u's have to be resubstituted. U cube over 3 plus c. I'm not writing the plus c. And let's write the final answer. The final answer is going to take a little bit of space only because when you bring in the secants, we have to be a little neat with our writing and maybe a little nice in our writing. The final answer will be right after this arrow. We'll plug in the u's, which are secant x. We'll have secant to the 11x over 11. Then we'll have minus 4 over 9 secant to the 9x. Then we'll have plus 6 over 7 secant to the 7x. Then we'll have minus 4 over 5 secant to the 5x. And then we'll have plus secant cube x over 3 plus c. And that should represent our final answer, and we can verbalize it. Secant to the 11x divided by 11. Minus 4 or 9 secant to the 9x plus 6 over 7 secant to the 7th x minus 4 or 5 secant to the 5x plus secant cube x over 3. You could get a common denominator across and bring everything under a unifying denominator. Isolate very likely a secant cube x and bring everything to a lower order or degree of exponents, or you can keep everything as this and it should be just as good. So that's it for this video. I wanted to just show you that the complexities that we presented in terms of the previous video can be overcome with a little bit of determination and by learning the rules and the framework I presented at the beginning of this video, depending on odd or even character of the exponents and the equation forms, tangents and secants or cotangents and cosecants. You've also seen that the framework is not difficult to apply. There are basically three things you have to do. Either at the beginning you're going to set aside something based on the type of framework. It is, you'll set aside something, you'll use some sort of trigonometric substitution from an identity, then you'll try to convert your integral into a polynomial substitution technique derived procedure, which will help you eliminate that which you set aside at the very beginning. Your function will get converted into a polynomial, which you have to expand and then integrate and resubstitute back, and that's it. Perhaps the most difficult part of this type of question is not the application of the framework, the three different parts of that framework or the three rules you have to do. It is perhaps having to expand things out when they become a little more complex. That might be the most difficult part. The application of the rules is routine and ordinary once you become accustomed to these type of questions. That'll be it for this video. Thank you for watching. Thank you for enjoying this video. Have a nice day. Bye.